Here we have a 5-inch dowel created by rotating the horizontal line y equals 2 about the x-axis. We're supposed to find the volume of the dowel. Now maybe you're saying, what is a dowel? Now a dowel is something you can find at the hardware store. You've probably got one in your closet right now. That's what you put your hangers on, right? So you can think of putting a hanger on this thing here to hang up clothes, stuff like that. This one isn't very long, it's only 5 inches. Now, in this example, I want to connect concepts that you've probably learned in a previous class to calculus. And this will help you in your homework when you get to problems where you can't use non-calculus methods to solve them. So the concept that you've probably seen before is how to find the volume of a cylinder. So let me draw a cylinder here. So we have a cylinder. Oh, I guess I should make this dotted back here to indicate that you can't really see it. There we go, something like that. Now let's say that our cylinder has height 5 and the radius of the base is 2. Now the volume of this cylinder here is the area of the base, which is pi r squared, times the height, h. So as you can see, with r equal 2 and h equal to 5, this gives us pi times 2 squared times 5, which is 20 pi. So the answer to this problem, is 20 pi. That's our answer, without the units. We'd have inches cubed for units. So what I want you to see is that this drawing that I have here is exactly this same drawing here, except for it's turned on its side. And what I mean by that is that here we'll draw the y-axis. Right, that's exactly what we have right here. And then the x-axis is coming up right through the center there. X-axis, that's our x-axis right there, right through the center of our cylinder. So first let's think about how do we actually get this three-dimensional object by rotating the line y equals 2 around the x-axis. So the way we do that is conceptually, the way that I think of it conceptually is you start with just this line y equals 2. And that's exactly this line here, right? This is exactly the line y equals 2. And then, so notice this what I have right here, this is 2D, right? This is two-dimensional. This what I have right here is three-dimensional. So the way we take the two-dimensional object and create the three-dimensional object is think of it as we have this area here. Let me draw it in blue. We have this area in blue here. And we rotate this blue region 360 degrees around the x-axis. So think of it as we're going around the x-axis. And let me draw that blue region in here. So think about this blue region in 2 dimensions, and if you were to rotate it 360 degrees, one full turn around the x-axis, you would in fact get this three-dimensional object the cylinder. All right, so now let's go back to the cylinder and think about what are we doing when we compute the volume of the cylinder. So there's our cylinder there. Now it really doesn't matter, remember how I said the volume was the area of the base. It really doesn't matter if you use the area of the base or really the area of any cross section. So let me just draw an arbitrary cross section here. So here we have an arbitrary cross section. I guess I'm not super happy with my drawing there. Let me make this a little better. Apologize for making you wait. There we go, looking a little better there. So now we can think of the width of this arbitrary cross section, the width. Think of it as like, you can think of this as a stack of coins, as you can think of, and the width of a coin would be our dx. That's exactly that dx there. So you see here, here's a stack of coins on its side. There's one of my coins there. Its width is dx. So the volume is the area pi r squared times the height. So adding up all these infinitely many coins with width, with really small width dx. Now we can do this exact same thing with the integral. So think about how we're doing that, right? So when we multiply this pi r squared times the height, right? Remember, volume pi r squared times the height. The times the height part, that's like adding up infinitely many of these cross sections with microscopically small width. That's exactly what the integral does. So the volume is the sum, or adding, right? Adding up all cross sections. So the sum of all cross sections. That's exactly what the integral does. Now we're going to sum them all up, and even this funny symbol is really an elongated s for sum. Somehow, no pun intended, over the years, this thing became this elongated s for sum. We're adding up all these cross sections. We're going to sum them up from 0 to 5, starting at 0 there, ending at 5. And these cross sections, they have area, which is like the top of the cross section, right? This top little bit right here, and then times the width, which will be dx, microscopically small width. So we have pi r squared times our width dx. Well, here we know what r is, right? Because see our r, right, that's exactly that distance there. That's 2, the line y equals 2. So we have pi times 2 squared, dx. Right. This is the area of this top part here. And this dx is just our little width. And so then we get the integral from 0 to 5, 4 pi dx, which is equal to 4 pi x, evaluated from 0 to 5, which gives 20 pi inches cubed.